So here I will be sharing a link with you. So you can just open that and let me know when you can see my screen. Is my screen visible? So if you could please vote into this, so we have a general idea about how to cover these topics during the session based on how experienced people are at in blockchain. Okay, maybe we'll keep this open for 1 more minute and then move on to the second question. Okay, so far I think most of you are completely new to this topic, so we'll be handling that accordingly. I will move on to the next question, which is you already had a session in the morning by the keynote speaker. So when you think of blockchain, what are the 3 words that immediately come to mind? So could you please type that in? So let's maybe cover these during the session.
It could be keywords that you have, that has caught your mind, or it could be buzzwords that everyone speaks
20
in.
over 8. 20 over
Ma'am, can we speak?
Yeah, sure.
It can be immutability.
It can be anything.
8. When you think of blockchain,
Immutability. It can be a shared ledger. It can be
Yes.
even a Bitcoin. It can be digital currency, cryptocurrency as well. So blockchain
Yes.
can be irreversible. Data which we are entering once can be add-on, but it cannot be updated. We can add on the blocks. The previous block is
Right.
linked to the earlier block and the next block. So we are adding the blocks, not updating the blocks. That's it.
Absolutely. Yes.
Right. Right.
So I see that, so this is a word cloud. If you can see my screen right here, a lot of you have been mentioning Bitcoin here, which is an obvious thing that comes into mind when we talk about blockchain. Bitcoin is inherently the first thing that comes into mind, being the most popular cryptocurrency that we deal with on the daily. So there are also some, could you please keep your mics muted? There's a little disturbance in the background. Please mute yourselves. Okay, so anyway, we see distributed ledger as one of the next most common.
Apoorva, I think you're muted. Could you please unmute yourself?
Hi, am I audible?
Yes, now you are.
Okay, so there are a lot of these words. These smaller words are some of the less frequently added words into this, the largest one being Bitcoin, which makes sense, and cryptography, of course, and linked lists, blocks of chain. So we'll be exploring what each of these words mean in relation to blockchain, in relation to Bitcoin, in relation to cryptocurrency in general. So privacy assurance, yes, and BTC, Bitcoin, yes, Vitalik. Oh, someone's done their homework. That's so. Let's just get into the session. We'll get into the presentation. So let's. Is my screen visible? Is my presentation visible?
Yes, Apoorva. Yes, it is.
Okay. So today we'll be covering these three topics in the first session. Blockchain introduction, what it's all about, how it came to be about, and objectives, users, and challenges. Who uses blockchain? What is the need for blockchain? Transactions and blocks. A little more of a practical implementation of how it works. A little bit of a deep dive into what exactly happens within a block. So blockchain introduction. Starting off, you all entered some words into the word cloud. Some of the common words may be not strictly limited to. Maybe we can talk about these ones. Digital ledger was the one of the more common words that was entered within the word cloud. So what is a digital ledger? We hear about all of these buzzwords. We hear about how blockchain has a digital ledger, but this is basically a ledger as we know it. Any bank, any financial institution, any kind of transactions, they maintain a physical record or a digital record of all the transactions that happen within the network. So a network or an institution. So a digital ledger is exactly what it says it is. It is a record of all the transactions that happen within the blockchain. So what happens in blockchain is a digital ledger is not maintained in one particular node. All of the nodes participating within the blockchain network has access to this digital ledger. So anybody can verify whether a transaction has been legitimate. And by transaction, I mean it does not necessarily have to be a monetary transaction. It does not necessarily have to be somebody transferring money to someone. It can be let's say a contract between two people, or let's say a land pledge, or anything. I'm pledging some donations, some goods to somebody, and all of that can be represented within a transaction block, and everything is represented within the digital ledger. So moving on to transparent. What is transparent? As long as the digital ledger is accessible to everybody within the network, everybody can verify that there is no illegal activity happening within the network, because before adding the block, a transaction block to the blockchain, it is verified by a majority of the nodes in the network. It is verified that there is no faulty transactions. There is no nobody is adding something without the consent of everybody else within the network. So this maintains transparency, and also there is no third party that is governing this entire network. So there is no need for somebody to monitor this constantly. There is this information is not limited to a central third party that is governing all the transactions. Everybody participating here will have knowledge of what is going on within the network. So this can be especially useful within let's say a use case where we have donations, which is what Nikhil and I usually research and work on. So donations, usually people don't want to be very they're a little skeptical about whether the money that they donate is being used in the right way, if it is going to the right recipients, or if there is a third party that is mooching off of this money, if it is being misused. So using a blockchain for this kind of activity prevents misuse of these funds, and so that everybody knows what is going on. Also distributed and decentralized, this kind of goes hand in hand. And also in terms of networks, Nikhil will be explaining this in a little bit of detail later, but distributed basically means that there is not one central entity that is controlling the blockchain. It is, the control is distributed throughout the network. Everybody has a share in, has a say in what needs to be done within the network. Decentralized also goes hand in hand with being distributed. So uh, the processing power is also distributed. Everybody uh, kind of processes for mining, which we will get into detail later. So everybody is using their compute power to verify the transaction's legitimacy. So this makes it more secure. So secure, like one of our participants already said earlier, blockchains are secure, they cannot be modified, and only new blocks can be added. So why it cannot be modified is because there is a lot of cryptography in play, and everybody is constantly monitoring the system, making sure that nobody is adding something that shouldn't be there because of the cryptographic algorithms, which we will discuss in the coming slides. And anonymous. So if you're handling transactions, you don't need to give out your personal data, say your Aadhaar number or your PAN number or anything of that sort, not even your name. You are just given an identity linked to a hashed address. It is just a digital signature. It is purely a digital signature, and you would not have to reveal any personal details about yourself, like let's say your phone number or email ID or your address. And this is also key factor in donations, because a lot of philanthropists do not want to reveal their identity, and they want to keep their donations anonymous. So also programmable. Smart contracts ensure that, so when we design a blockchain, we have a block that is added into the chain. So we can set conditions to ensure that these blocks are automatically added to the blockchain when a set list of conditions are satisfied. Let's say I say that I am going to pledge so and so amount into this organization. So if that condition is satisfied and it is verified by the receiver party, this block of transaction is automatically added to the blockchain without any manual intervention. I don't have to explicitly go and add this into the chain. So there are a lot of uses for this programmable blockchains. So this is also a major innovation. A lot of industries have been using these in supply chain management and a lot of other managing transactions, streamlining transactions basically. So now that we have some of these keywords in place, let's get into how exactly a blockchain works. So a transaction is requested first. Let's say it's something very simple, that I have paid Nikhil 30 rupees. So this data, along with a lot of other details about the transaction, let's say a timestamp, a hash of the previous block in the blockchain, the size of the data that is contained within the block, and a lot of other data that is important for verification within the network. Maybe it can be your public key, it can be some kind of identifying factors, or anything else that would be needed to make sure that this transaction is legitimate. This block is created. A block is basically a file in simple terms. So this block is available to every node within the network, within the blockchain network, whoever is participating. So these entities within the network can validate this transaction. They can say, yes, this is actually a legitimate transaction. They are actually transferring these funds in a, this is a, there is no illegal activity happening here. There is no uh, nobody is trying to spoof this transaction. Nobody is trying to make use of double spending using the same token. This is a fresh token. So this kind of verification is not done explicitly, but these are generated into a bunch of mathematical equations that all of these nodes can solve. So solving these nodes is what is called mining. So for the expense that they spend, the compute power or the time that each of these nodes within this network spends, they are spending their CPU cycles, they're spending their time, there some kind of intense activity is happening. So they are compensated with a reward. So this is what we call proof of work, or there are a lot of other consensus mechanisms. So based on their work that they put in to validate this transaction, they receive an equivalent amount as a compensation. So this is what is called as mining, crypto mining. So once this transaction block is deemed suitable, deemed fit to be added into the blockchain, only then it is added into the blockchain. Unless it is suitable, it is discarded and it is called an orphan node. They cannot be added into the network, and because it does not have a sufficient standard of validity. So once it is added, we can call the transaction complete. So moving on, Nikhil.
Um, Hello everyone. So in this section, we would be speaking more about consensus mechanisms and the general networks on which blockchains are deployed. So let's start about networks. When we speak of networks here, these are the networks of how the systems are implemented, and they're broadly spread into three categories. So Apoorva, could you please show them the network types? So yeah, as all of you can see on the screen, the three broad categories of networks that we see or use are centralized, decentralized, and distributed networks. So we will start with centralized networks. These are one of the most common architectures that we always see. So when we refer to client server architectures or the unidirectional architectures, these are the centralized types of architectures, and these are the most common architectures where you have one central hub or a central node which is connected to all the users. It processes their data, processes their requests, collects and stores all this data, and in return gives the results of all the requests that these users make. So in a centralized system, what happens is there is one single entity that is in control of all the data being processed in the network or the system. And as you guys can guess, this also automatically leads to a single point of failure. That means in this kind of a network, in a centralized system where you see there's just one hub node, which is the main, if that hub is taken down by an attacker or by a malicious intent, or if you perform a denial of service attack on that single node, that can take down the entire system and render the service or the network unavailable for the rest of the users. So, why would anyone use centralized systems? So, these are traditional architectures we've been using till now. It's because of their deployment and their development speeds. These architectures are very simple to make. All you have to do is make one server. That server process all forms of requests, and all the user inputs just enter these servers directly, and all the answers return from these servers straight back to the users, and they get their requests. So in this way we achieve a centralized system. Because of the high development speeds and high deployment speeds, these are most trusted, but they can have single points of failure, and that's why these are lacking, and we had to move on from these kind of technologies. One of the other main gripes with the centralized system, it would be, is that the central node is in control of all data. So security, privacy, transparency, all of this would either be the responsibility of the central node, or these concepts simply might not exist. Privacy might not exist when a central node is observing each and every single action or step of your data. So the next system that we will speak about are decentralized systems. So as many of you have already answered in our Ventimeter voting, we have seen that decentralized is one of the main keywords that is associated with blockchain. And it is rightly so, because what decentralized means is that there is no single point, one single hub saying that is the center or the certifying authority. There are multiple nodes which are in tandem or in connection with each other, and all of them have equal authority to verify transactions or serve the user requests. So what happens is, in such a scenario, even though one of the nodes is affected or let's say compromised by an attacker, the rest of the nodes can still interoperate and serve the request to the users, saying that there is a higher uptime than centralized systems. And this also means that we do not have to depend on one central authority for all our data processing. Since there are multiple distributed or let's say further spread central authorities, which there are multiple of them. So you can always expect a response or a request from the servers without any failures. So the problems that you might face with such a system is it is a complex system. It would take high development times. And let's say I'm just giving a very brief example. If one had to write a centralized server system, a client server architecture, if he would take any programming, functional programming language like let's say Python, and he uses a few famous libraries like Flask and Django, it could be these codes could be written and deployed within 20 lines or 30 lines of code. I'm not saying those 30 lines of codes are very simple to write, but I'm saying the effort required or the amount of processing required would be minimally lesser. Whereas when you shift to a decentralized system, you would have to write down the consensus algorithms, which we will speak about later. So these consensus algorithms would take more complexity and more time and more thought from the programmer and all the stakeholders involved in the system creation. And then they would have to arrive at a common agreement and program it. So it would be taking higher development and higher times of what do you call that? Higher development times and higher preparation times. One advantage of decentralized system is their high scalability. So unlike centralized systems, which are like vertically scalable, decentralized systems are vertically and horizontally scalable. That means they can take larger amounts of traffic and they can spread into multiple or more nodes so that they can serve traffic from other directions as well. And the last kind of network that we would speak here are the distributed networks or the distributed systems. And these systems, as you know, every single node or participant are equally important in the resource. So everyone has equal importance and equal duty towards the system. These are very difficult to develop because these are peer-to-peer networks and would require high interoperability and high connectivity. So it would be difficult to develop and implement compared to the other two systems that we have seen. Whereas the distributed systems have the highest advantage of maximum scalability. Since every new node that is added directly takes over ownership of certain amount of activity. Let's say there are 10 nodes in a system and each of them have 10% of work. Let's say another 10 nodes are added to the system. All the nodes equally divide 5% of the work, complete their 5% of the work, and the whole process that way is sustained. So these are highly scalable and these are very good systems if you want to implement for large and robust applications in which the time of development is not of great concern. So what happens since every all the peers have shared responsibility? What happens is distributed systems have high fault tolerances. They have very high transparency because every single node is responsible and every single node's actions can be seen by the public or by all other nodes. Extremely scalable, like I already mentioned, and these are also secure and fault tolerant because even if you take down half the nodes, the other half of the nodes would still work and they would still, supply requests to the users or the systems. So let's typically compare these three, network types on a few factors such as scalability, time to development, and, fault tolerance, evolution. So when you see fault tolerance, it says that centralized systems have very high fault tolerances and distributed systems have the least comparatively. It's like I explained, since let's say there is a wheel and there are the center of the wheel and there are spokes to the wheel. So the outer wheel are the users and the spokes are the connections. And when the center, the hub of the wheel breaks, the rest of the spokes just shatter, fall down, and the wheel collapses. So that's how a centralized system works. It is the one in the center, and when that breaks, all breaks loose in that system. Scalability. So, like I told you, centralized systems have low scalability. Even though You might argue that most systems that we use, Amazon, Facebook, Google, YouTube, Twitter, all of them are centralized architectures to the current day, and they are highly scalable. Then why do they say it is low scalability? So here, in context to scalability, what happens is they are highly scalable vertically. Instead of putting up one server, they deploy hundreds of servers across the globe in a centralized system. So what they do is, they are just increasing their manpower. If we had to, take similes, they are just increasing their manpower to do the same work instead of increasing the efficiency of doing work. Whereas when you see decentralized and distributed systems, or let's just take distributed systems as an example for now. What happens here is, in the distributed systems, every single node or every single peer takes equal responsibility. So they are efficiently dividing the tasks at hand, and they make their processing faster rather than just adding extra nodes to do the work. So scalability in distributed systems is due to efficiency of the programming, and in centralized systems is due to the higher number of physical servers, or the cloud infrastructure that they might use. They scale up in those contexts. Now when you go to maintenance, a centralized system which might have a simple code base, it would be easier to maintain this code base, because we know that there is one central architecture which you have to look for. Any discrepancies, any kind of malicious activity, it would generally be found there, and it has a designated post, so you could easily find where the bugs might be located. In a distributed system, you would have to increase that opportunity or bug finding task n-fold. So if there are 100 peers, you would have to check all 100 peers for their tasks. You would have to evaluate or like do security risk analysis for every single peer. And only when you have the complete confidence, or when you fix the bugs in various peers, that's when you could go further or move further with your system and production. So evolution here, let's say it says low for centralized systems. I have a reason for this. It's because till now centralized systems have been evolving from the time or the inception of the actual internet, where the World Wide Web consortium was formed, and how we use internet as to this day. Everything is a huge graph and involvement which goes like upstream, and that is all because of centralized systems and client architectures. So the biggest perpetrators or the biggest users of centralized systems that all of us might be facing or might be using are banking systems. So it is not uncommon to us. We have seen that while performing transactions online, that there are high, chances of servers crashing. We get error messages saying could not perform or could not go forward with the transaction because the servers timed out. This is because of their low scalability and their limitation to handle very high capacity traffic. So that's why we have peaked our centralized system technology as of now. Innovation is always a part, but we have reached a zenith from where we could just flatten the curve and not just uprise. And what will evolve from now on, what is actually a more transparent, secure, and a better foundation for the future would be decentralized and distributed systems, which coincidentally blockchain is using from the 1990s, but it not get a complete gripe like Dr. Anand mentioned until the late 2000s. And once it got popularized also, it is still debunked in a lot of places. It is still not considered as a novel or niche technology. They still have their hindrances or inhibitions to this technology. So blockchain works on a few consensus principles or consensus mechanisms, like we discussed. So these consensus mechanisms, what are they? Like everyone keeps saying consensus mechanisms, but what are they actually? So, like we have seen, blockchain is a decentralized and a distributed system. So there are multiple head nodes which are responsible for authorizing or validating transactions. So I will take a simple scenario. I will explain how a transaction works, and then we will see how these consensus mechanisms validate and add these transactions to the blockchain. Apoorva, if you could please move to the next slide. So, in the meanwhile, so we'll talk about a simple scenario of how a blockchain transaction works, and then we will see why a consensus is important and what are these consensus. So, let's say Apoorva and I are trading, and I am the sender or the initiator of the transaction, whereas Apoorva is a authoritative node or a miner in terms. We will explain more of these terms later as we touch upon those sections. For now, we will just take a simple example as to how this works. So let's say Apoorva is a central authority, a certifying node, and I am a initiator of a transaction. I am just a user in this system. I would like to pay XYZ 1 Bitcoin. That is the transaction that I would be using, or any other cryptocurrency that is comfortable or the system uses. So since Apoorva has mentioned that it is a anonymous and a private and a secure mechanism, I do not have to give out or indulge in my personal details. I do not have to give them my bank statements or my bank account numbers for them to take money. I can do that myself. I will be given every person who wants to trade in cryptocurrency has this important wallet. So every user has a wallet. A wallet is basically, like the name suggests, a container to store your cryptocurrency tokens, or the monetary values of the cryptocurrencies. What happens is, in these containers, these wallets, they do not have your name, they do not have your account numbers. You are just a user, and it has a hash value. Let's say it could be a 32 or a 64-bit hash value, and this hash value is your identity in that system of cryptocurrencies or blockchain. This hash value, which you will use, will be your identifier for conducting or performing transactions or receiving monetary goods or other transactional data. So you will use this address and the receiver's address. Every user has a unique hash value address. So we'll enter the sender address and the receiver address, and then you will send the amount of tokens that you want to send to the receiver. What the certifying node in between does is, they have to check if this transaction that is happening is valid. They cannot see my personal data. They cannot see the receiver's personal data. All they can see is the ID, the hash ID of the sender, hash ID of the receiver, the amount that the sender wants to send to the receiver. What they will do is, first they will check the public ledger. Once I start initiate the transaction, a block is formed. So my monetary value is inside that block, and it has to go to the receiver. The certifying or the central authority, what they do is, they see the public ledger. They first confirm the sender and the receiver addresses, making sure that they are a part of the system. They are not any malicious or illegitimate users. Once that is done, they will see. So, like how our money has serial numbers printed on them as to this day, that is used for the purpose of tracking money or tracking the liquid currency that is moving around. The same way, even blocks or even the tokens or cryptocurrencies have these kind of hash values, the numbers to keep track of these tokens. What happens is, they verify if this token has ever been used before. So they will check. And since blockchain is an immutable technology, once this token or this crypto has been used or the transaction has been previously performed, you cannot perform this transaction again, and it will debunk the whole transaction as an illegal one. Once it checks the public ledger and it finds that these coins have never been spent before, and these two parties have never transferred or received tokens amongst themselves before, when they see that it is a unique transfer and it forms a unique block, that's when the central authority or the miner validates this transaction and then adds it to the blockchain. So on a high level, this is how a blockchain or a transaction is performed and added to the chain into the public ledger. So the ledger is updated with all the transactions and their history without involve or without revealing any sensitive information except for just the hash values. So how does this, I said the central authority or the lying node validates the uh, transactions. How do they validate these transactions? By using consensus principles. So when we see that consensus principles, uh, they mean that an algorithm is put in place which is favored by all the nodes or all the certifying nodes, and they have agreed upon mutually that we will follow these algorithms or these set of rules, and only if any transaction falls within these set of rules or like satisfies all the rules stated in the consensus algorithm, that's when a transaction or any kind of block which has been formed is valid and is updated into the ledger and added into the chain. So these consensus algorithms, they used to have a common point of judgment or agreement, and it should be a fair and equitable process where it shouldn't favor any of a particular user group or a user node or any of the particular central authorities. It should be fair and just to everyone, and with the help of smart contracts, there is no human intervention at all in this entire process. All these programmable logics are written into a smart contract and deployed on the blockchain, where any transaction that occurs, these smart contracts which are sitting in these central nodes will check if all the points of the transaction are valid, and only when they are valid they will be added to the ledger. So we have mentioned a point here saying it prevents double spending. So double spending is an interesting or a very tricky situation that occurred with the inception of blockchain and other cryptocurrencies or digital currencies, and uh, we have to use consensus algorithms to prevent that kind of scenario. So double spending would be a scenario where, let's say, a person has two 500 rupee notes. One of them is original, printed by the RBI, approved by the government. Another one is a counterfeit note. And let's say the receiver has no knowledge of this at all. So if the spender has just 500 rupees of actual monetary worth, but he has 1000 rupees of physical monetary worth, where one is a counterfeit, one is an original. So what he does is he can use the counterfeit to perform a transaction, and if the receiver cannot clarify that if it is a original token or a counterfeit token, then that transaction stands. That means if the receiver has accepted the monetary resources and does not find any fault with it, does not raise any dispute, that transaction stands. Even though it is illegal, it was performed technologically right. It was morally wrong, but technologically right. So it always stands as a legal transaction. And because of that, even though a person has original currency with the same number and he tries spending it, it will be rejected in the public ledger, saying that this cryptocurrency has already been spent or this transaction has already previously occurred. You are trying to perform an illegitimate transaction. And even though he has an original token on which he invested money, he is still denied of using it or performing transactions because of such double spend activities. So to remove these kind of double spends and other problems that might occur in a crypto background, we use different types of consensus algorithms or consensus mechanisms which validate and record transactions into the blockchain. So now we will just look at the types of consensus algorithms. So like Apoorva and like Dr. Anand have already mentioned, there are numerous ways of deciding or reaching out to a common agreement on how to validate or how to transact in a crypto block. Uh, so let's see. Proof of work, proof of stake, Byzantine fault tolerance, and directed acyclic graphs. These are the four main kind of consensus algorithms or mechanisms that people have been using. Okay. Yes, so Mr. Hemraj, this diagram is copyrighted to Mr. S. Chandramouli. We have given him credits later in the section. So I hope we could continue with the session. Proof of work is a consensus algorithm which basically states that if a transaction has been performed or if a transaction has to be validated, what has to be done is the miner or the user has to perform very complex mathematical computations. So we will speak more about these mathematical computations in the later sections and in the next session, where we will go in detail and see how these mathematical computations help or how these sessions actually work. So proof of work, a miner has to solve complex mathematical computational problems, and once he arrives at an answer which is close or lesser than or equal to the actual intended answer in the blockchain hash, if both of them are very similar or match, it means that the miner or the user, whoever performed this complex mathematical problem by dedicating his CPU cycles, he is rewarded with a Bitcoin or with some form of cryptocurrency or an incentive. So we see that proof of work is the major form of validation for the Bitcoin. Bitcoin is the most popular cryptocurrency as of today, with its worth reaching $35,000 a coin approximately. So proof of work is the consensus algorithm that is used by Bitcoin. Here we can see that it has very high energy consumption. This is one of the reasons why Bitcoin, or let's say blockchain mechanisms, have very slow adoption rates, because they consume lot of CPU cycles, lot of GPU cycles to perform complex, mathematical problems, and this draws a lot of power. So it could draw up to 67 kilowatt hours of power in an hour. And imagine such an extended period of use, it would draw very huge amounts of power, which would not really be very economically beneficial. The amount of, let's say, crypto rewards or bitcoins that you get out of mining is very negligible compared to the power and the electricity bills that you have to pay to mine these. So that's why when someone asks if they can start mining with the laptop they have at home, of course yes they can, but it is not really a very profitable venture. It is a very small scale profit compared to the large scale investment that you have to put in. It also has very low transaction speeds. We can see it's in the range of 7 to 30, and has a high transaction fees. So a transaction fees here stands for the amount of computational input that you are giving, the electrical input, the computational input, the amount of computing power that you are dedicating for this validation purpose. Next, we go to the proof of stake. In a proof of stake, what happens is, how they decide validation is by giving the validation duty to the node or to the miner with the most stake or the most asset in the blockchain. So let's say there is a crypto system or a blockchain with 100 coins, and let's hypothetically think that one user has around 31 coins, or it's just a random number I'm picking, or 35 coins in the whole system. So he is the sole majoritative user in this whole scenario, where he has the highest number of coins. So if there are any double spends, or let's say if there are any illegal or faulty transactions, he or this person with the highest number of coins would lose his money. So if he loses his money, he would naturally drop value, and his stake in the coin base or in the crypto system would fall down. So prevent that, what happens is the consensus algorithm asks this miner with the highest stake or with the highest investment or highest loss factor, the consensus algorithm would ask him to validate the what do you call that he would ask him to validate the transactions. So what happens in this base is a person who knows he would lose all his money if the answer is wrong, or if he validates an illegal transaction. He doesn't want to lose his personal assets because of someone else's malicious activity. So they would be more careful, morally speaking, more careful with their transactions and their ledger updates. So this consensus gives them the authority to validate any transactions, and with that power, they would validate and update the transactions in the public ledger. Now, let's speak about two other different kinds of consensus mechanisms, which are not generally, not implemented as much or as widespread as proof of work and proof of stake. So we will start with the Byzantine fault tolerance. So before we go with the Byzantine fault tolerance, there is a problem that this algorithm solves, which is the Byzantine soldiers problem. So the diagram is minuscule here, but if you can, from the outer mergers or borders that you can see, if there is one central city. So this was the problem that this algorithm was intending to solve. If let's say there is a city of with lots of gold in it and lots of rich lands, and it is being protected by outer walls, and then there is an army which is split into multiple different parts, let's say 4 parts, and they have covered across the city. These armies, let's say there is one general or one leader in one of these 4 sections of the army who has malicious intentions, and who has connections with the city that they want to conquer, so that he compromises his army. So now let's say these 4 portions of the armies are validators or the certifying authorities in a blockchain, and the central city that they want to beat are validation transactions which they have to validate. So what happens is, even if one of the nodes out of the 4 are faulty, or if it's compromised, the Byzantine fault tolerance mechanism makes sure that the number of honest nodes, or the number of nodes which are uncompromised and still work according to the consensus, they have to be more than the number of compromised nodes, and whatever these 3 nodes or the honest nodes agree upon, that would be validated as the valid transaction, and the opinion of the compromised node would be taken into consideration but will not be updated into the final ledger. So that's how a Byzantine fault tolerance works. So what it principally states is that the number of honest or uncompromised nodes should be 2/3 of the total node in the blockchain network. And when there are the 2/3 of the total nodes in the blockchain network are still uncompromised, even though there are compromised nodes which are trying to validate transactions, the rest 2/3 of the nodes can prevent these illegal transactions from being validated by the compromised nodes, and they could update only the valid and the legal transactions into the public ledgers and add them into the blockchain. We see that Byzantine fault tolerance has lower energy consumption because of the way the algorithm was designed. So even if 2/3 of your nodes are using a right amount of power, since compromised nodes would be sourced from another source, the power would be sourced from somewhere else because they have been taken out of control. 2/3 of your normal power consumption is still enough to transact and validate all the transactions. You also see that there are high number of transactions which are possible using Byzantine fault tolerances. and have very low transaction fees. The last and like not the least, but the most novel kind of consensus mechanism which is being implemented as of today is the directed acyclic graphs. So rather than explaining it as a consensus algorithm, a directed acyclic graph is a data structure. And this data structure is being modified and implemented to replicate or act like a distributed ledger. So directed acyclic graphs, what happens is in a blockchain, when there are serial transactions, every block is hashed with the previous block and new blocks are attached to the older blocks. So it forms a continuous interlinked chain of blocks, and hence it's called a blockchain. In directed acyclic graphs, all these transactions are linked to each other too, but instead of forming chains or like a serial linked list, what happens is they form trees. And in directed acyclic graphs, you don't need one central authority or one certifying node to come and validate these transactions. Every transaction is self-validatory because the consensus algorithm is applied on the transaction rather than one particular holding node. And every transaction that is linked to each other in the form of a tree, what happens is it uses the same principles or the same advantages that blockchain had. It would hash the value of the previous block so that it makes the next block even more secure, so that the whole chain or the whole tree or the part of the tree, it will not become tamperable. And that's how a directed acyclic graph works. As you can see, IOTA is one of the companies. They are trying to develop this technology, take it further than what it is. It is a very nascent consensus algorithm as of now. Not many people work on these techniques, but this can be a viable replacement for the distributed ledgers that we have right now. So let us move on from the types of consensus algorithms. So just to give you a brief overview of why we require consensus algorithms, it is because we can maintain uniformity of how or what we call a legal transaction and what we call a illegal transaction. So once you can clarify this and everyone agrees upon the set rules of what is legal, what is illegal, it becomes easier for us to implement those as programmable smart contracts and deploy them on the blockchains, which minimizes human effort and validates transactions in a much more transparent and secure fashion. Thank you.
So we've learned quite a lot of about blockchain in the past half an hour. So we will get into how blockchain actually started. There is this general idea that blockchain is something very new and very up and coming, but it has been around since the early 1990s. And the first implementation of blockchain was by a cryptographic researcher in 1991. And previously, they would use one transaction block for one document. But later, incorporating Merkle trees into this would allow you to create a transaction block for multiple documents as a single block. So you would be saving on the space overhead. As we know, when we're storing a block, there is a lot of extra metadata that goes into this. But adding multiple documents within a single transaction reduces that overhead, in turn reducing the effective size of the blockchain. Am I audible?
Yes, Apoorva, yes, you are.
Yeah. So, like it was mentioned in the previous session as well, we know about Satoshi Nakamoto, but we do not know if they were a person or a group of people. But they released this first white paper in for Bitcoin in the year 2009, and I will send the link in the chat as well. It's a really good paper that explains how the Bitcoin was theoretically built to be a form of transferring digital currency. Uh, after that, there has been a lot of developments. After this was handed over to corporations, a lot of innovation has come to in this area. But this was at the time a very revolutionary method of handling blockchain. So in 2010, there was the first Bitcoin purchase in the marketplace, and then it had a very whopping surge in users and purchases. So by 2013, it was already valued at 1 billion, and this kind of gave a motivation to a lot of other cryptographic enthusiasts and developers to come up with more platforms like Ethereum, R3, Hyperledger, all of these other platforms that people wanted to experiment with, get get more into cryptocurrency, get more into blockchain. So this was kind of a stepping stone into the cryptocurrency world. And as we know right now, blockchain has penetrated a lot of areas in technology, a lot of areas in business as well. So as of 2020, cryptocurrencies themselves own a market share of 20 billion, that is 0.025% of the global GDP. And this is just the cryptocurrency market. A lot of other technological implementations of blockchain has come up in various different companies that are dedicating their time and research into how to streamline their businesses and processes within blockchain, which we will see in the next users and adoption section. So what what is the motivation for blockchain? What makes users want to change their way of working into blockchain? So maybe Nikhil, go quickly into the objectives in the interest of time. I think we have.
Yeah, yeah. Could you just give me a second? Um, yeah. Am I audible?
Yeah, yeah.
Yeah. Thank you. So, what are the objectives or the motivations that one would, require, or one would really need to adopt blockchain technology? Why would one adopt blockchain technology? What are its advantages? Okay. So security, transparency, elimination of third parties, non-repudiation, immutability, and faster settlement. These are a few key highlights or key terms of why blockchain, is being used these days. Security as a primary concern. So a lot of people had the misconception that blockchain had just two purposes. One is for cryptocurrency, that is Bitcoin, and one more is cyber security as a domain, saying if I put my data into a blockchain system, it is completely secure. Both of them are myths, but security is still one of the foremost reasons why a blockchain is preferred. And this is majorly thanks to the advanced cryptographic and hashing algorithms and mechanisms that blockchain puts in place. The whole system or the whole technology was designed with cryptographic algorithms or cryptographic concepts as a basis, and then on basis of these secure cryptographic algorithms, they developed furthermore, and we have the present day blockchain technology. However, we have transparency is one of the most important aspects, according to me at least, for why a person would implement blockchain. So transparency majorly can come from the way blockchain is implemented using the distributed ledgers. So in a distributed ledger, it depends on what kind of implementation again that we are using. There could be public, private, or hybrid systems. Let us just consider public systems for now. So a public system where everyone and anyone can view all the transactions that have been performed without revealing any sensitive data. That's how the security and the privacy is maintained. But also, it can see that all the transactions have been recorded in a suitable format, in a very readable and extensible format, and people can always see what transactions are occurring. So let's say one day your friend comes up to you and says, I will share let's say so and so percentage of my Bitcoin with you. So if you go to that Bitcoin or that blockchain system's public ledger and you want to see if the tokens that your friend is buying or willing to send you, if they are already double spent, you could see if if these tokens have been registered already or previously transacted before. If they are, that means he's sending you counterfeit tokens. Or you could also come up with other use cases where you could prevent illegal transactions with the virtue of the public ledger. So that's how transparency comes into picture. What blockchain does is it can build trust for us, and it can build trust by eliminating middlemen or third parties. So let us like hop on to the example again, where we take our banking system, our traditional banking systems. So our banking systems, even though it looks like there are only two parties, the user and the bank, which is not the case. There are always third-party middlemen. Let's say the UPI apps we use, even though they don't directly have control over our bank accounts, they can still access the data of what transactions we are performing, to who we are transacting, how much, when, where, all those details, you know, geolocations, everything. They might not reveal the details to us because it's not an open source implementation. So we don't know, or we can't trust how much of our data they can gather. Whereas in blockchain, it is just a two-party interaction, a sender and a receiver. Sender has his own unique hash address. So next time when I have to send it, let's say I am buying goods online using cryptocurrency, I do not need to know, if my receiver, whoever I'm buying the goods from, if he is a male, female, which city does he live in, postal codes, pin codes, his IFSC codes. I do not need any kind of information like that. Uh, so what happens is you just have the hash address, and this hash address is the identifier for you as well as for the other transaction party. And what you do is you just enter these addresses in the respective zones in the trading platform. It could be various trading platforms, they might have different ways of implementation, but fundamentally, if just the sender's address, the receiver's address, and how much amount he wants to transact, if this information is present, that is enough to perform a valid transaction. And it completely cuts out the middlemen. Cutting out middlemen doesn't just build trust, but it also economically benefits the organizations. Processing charges, processing time, extra processing fees for all the middlemen, all of these three factors, they directly are reduced to nil with the implementation of blockchain technology. The next we would be discussing about is non-repudiation. So, like, you guys have already mentioned, like all of you ladies and gentlemen have mentioned, non-repudiation, something that has been put in the blockchain will not be changed. Non-repudiation and immutability go hand in hand. We will speak about both of them in the same breath. So once a transaction is validated, or once a transaction is performed, updated in the ledger, added to the chain, it, I would not say impossible to break it or tamper it, but it is highly improbable that one would have or achieve enough compute power to change it. I will explain further on in the session why I would say it would be highly improbable and how much compute power you would require to actually change and make your illegal transactions as the viable legal transactions. So non-repudiable, you cannot change the data that is already present in the ledger. Once recorded, it is a permanent record. You cannot change it, you cannot delete it, you cannot modify it. You could just add new transactional blocks to the chain. That's all. And faster settlements. This happens by the virtue also of cutting out middlemen and having no middle processing layers. It is just a two-phase transaction or like a single-phase transaction where it goes from the sender to the receiver. So let's say generally in a bank scenario, I would be comparing most of my practical examples to a bank, as I feel when we talk about blockchain and cryptocurrency, a traditional bank and money is what a centralized or a real world system parallel that can be drawn. So let's say in a bank scenario, if you perform an NEFT or an RTGS system, or you deposit a check, generally, at least if not now, if now that we are modernized, if not now, a few years ago, you would take some time to process it. So if you drop a check into your account today, maybe the bankers or the cashiers would say we need a business day or 2 business days to process this amount for it to be credited into your account. With the help of blockchain, it is as instant as a UPI transfer and more secure than a UPI transfer. So what happens is sender directly sends the money to the receiver. It has to be validated in between, of course. It has to be validated. It has to be a legal transaction, and only then is it updated in the ledger and the money is credited to the receiver. But this is a much faster and a securely automated process compared to the present day, centralized banking systems and how they process money through multiple parties in between. So these are a few primary objectives or motivations of how blockchain can be helpful, or the sectors where blockchain could be useful. And let us take a look. Apoorva will help us look at how these objectives or motivations have motivated a few companies to adopt blockchain.
So there has been a general misconception that has been built over the years, even during our research, and we've come across people who question whether what is the need for blockchain? Why isn't it just used for illegal purposes in the dark web? Is there a legitimate need for the use of blockchain? So all of these companies and many more have been revolutionizing their business, their operations by implementing blockchain within their daily operations, their daily technology. We can see like around 10 sectors within this list. So bank and finance, this is a given. This is like an obvious use for blockchain, streamlining whatever records, ledgers, everything can be handled very smoothly within bank and finance sectors. Supply chain, like I earlier mentioned in smart contracts, this would ensure that everything goes smoothly without manual intervention, as long as things are being completed, as contracts are being handled, they are automatically added into the blockchain, they are maintained as a permanent record. So companies like Walmart, Ford, a lot of other companies have been implementing supply chain blockchain use cases. And in healthcare, now we have our vaccine provider for COVID-19, Pfizer, and a lot of other, the FDA, CDC. The benefit of using blockchain in healthcare, you can easily track patient claims and the status of their claims without having to reveal any sensitive healthcare data, any sensitive patient information. Everything is maintained within the blockchain and is accessible. You can check the validity of the claims, you can check the status of the claims without having to have it be tampered with. This also has a very good benefit for auditing in healthcare. So everything is available easily for the auditors, and they do not have to. There is no suspicion. There is no cause for suspicion here, whether or not everything is being maintained up to code, or whether their money is being utilized sensibly. Everything can be engulfed within this bubble. So insurance, there have been a lot of companies like MetLife that are uh, using blockchain in insurance capacities for one particular interesting use case was that they would track, if suppose person ABC has a deceased relative, they have a mechanism to for you to be able to easily track whether or not the deceased relative had an insurance plan. If not, these companies would easily be able to track that and provide a new insurance plan for them. So tracking older insurances records, everything would be made so much easier using blockchain mechanism. Energy, this is a surprising sector. but there is being like this is an ongoing research area for a lot of these companies, Siemens and Shell. They have been using Shell has been using this for crude oil trading. So blockchain with crude oil, instead of handling monetary transactions, you would be trading it with crude oil. So Shell has been researching this area, and also some companies are using blockchain to track the energy consumption, to keep a record of how much electricity is being consumed in what sectors of the area. And also in real estate, this is also, like I earlier mentioned, you would not need to have an explicit file paper ledger to maintain all the records, all the contracts. This would minimize the paper use and streamline the entire process by having a blockchain mechanism to store important documents, and even pledging land as an asset instead of money, or like we previously saw crude oil. Real estate has been using land as a pledge within their blockchain. And for trade, this is also a very kind of a default explanation for it. Trading uses a blockchain as finance would. And a lot of governments, although the Indian government has not been very enthusiastic about bringing in blockchain into our daily operations, a lot of governments have been implementing blockchains for integrated with smart cities, tracking finances and electricity. Governments like Dubai, Singapore, uh, South Korea, a lot of countries are making stands to try to expand the innovation that is being used with blockchain to increase the efficiency of how things are handled within the government. So, and also IoT and blockchain, as we have all these other new up and coming cutting edge technologies like IoT, cloud computing, integrating blockchain with such applications can make them more efficient. And cloud computing has this other branch. As we already know, we have IaaS, PaaS, SaaS, software as a service, platform as a service. There is this new up and coming area that is being researched by companies like IBM, that is called BaaS, that stands for blockchain as a service. Basically, you would not need to look into the nitty gritties of setting up a platform or setting up your cryptocurrency. Everything is handled within the platform, that you can just access it over the cloud and program your own blockchain implementation, customize it as you need it for your business or your project, whatever you are implementing. So this can lead to a lot of innovation in the blockchain technology sector, as a lot of developers could have problems with implementing blockchain systems, linking the servers and everything, linking the nodes and everything. So this could make it a lot easier and a lot streamlined to develop blockchain applications. Also, travel. A lot of big airlines like British Airways, Singapore Airlines, all of these airline companies have been using blockchain records to track their users who are frequent flyers, maybe come up with loyalty plans for them based on this. Since everything is maintained in a distributed ledger, it makes it easier for this would obviously be a private blockchain accessible only within the airline networks, but this would enable them to be able to streamline the search for their data, how to uh, better optimize their loyalty plans, better optimize their uh, make sure their customer base stays with them. They can optimize these things in their business. So as we see, these are some of the a few of the already implemented companies that have been using blockchains, adopted blockchain, but there is a lot of room for improvement. And there are also a lot of factors that influence user adoption for blockchain, because there is a lot of apprehension about this. So some factors can be, one of the major factors will be political regulations. Some countries might have very strict regulations about not using blockchain. There are some countries where you cannot it is illegal to trade in cryptocurrency, or uh, as long as it is not regulated, as long as there is no guidelines for use, people are more skeptical about using new technology because they do not know whether or not they can trust it, whether or not it is approved for valid use. So, and also the other problem can be not regulating, like for example, our currencies are overseen, how the rise and fall of the value in our currency is overseen by an entity, but that is not the case with cryptocurrency. So economic costs and volatility, people are not very confident about investing in something like cryptocurrency, purely because of how volatile it can be. There is not one easy way to predict the rise or fall of it. Very similar to the stock market, but this can be a little more, uh, as users would need a lot of background understanding before they get into this. This can also influence people using it, and also privacy concerns. Although blockchain by its essence, it does not reveal your personal information, although it has the feasibility for you to do that, there is always the concern of a third party not following guidelines that have been, if there are no guidelines implemented, they can always say, hey, give me your social security number or your Aadhaar number, so that as long as that is not regulated, people will have privacy concerns about using this kind of technology, or also the lack of understanding of how it works and whether or not their data is saved somewhere in a secure place, because we are used to an age old system of a centralized implementation where one entity governs your data, your operations, your transaction. So this is a very wild shift for most users because they would not be used to something so starkly in contrast with something that they've been so familiar and so used to. And also technical quality, although uh, blockchains give a little more, a lot more control over users data. So if I am participating in a blockchain, I know what is happening in the blockchain. There is more user control for me, and I know all of the transactions that are happening in the blockchain. All of that is there, but unless I have an understanding, a background of what it is, how it works, it can be difficult, as our schools do not usually include this in our curriculum. Our engineering, computer science does not include blockchain as a course. So integration with existing systems can be difficult because nobody has been trained for it. And also it can be a little difficult to integrate a decentralized or fully decentralized distributed system on top of an existing centralized system. That would defeat the point of having a separate decentralized system, right? So this all of these factors kind of, although these have the good and the bad in all of these points, there are a little bit of, maybe a little bit of more awareness, a little bit of experimenting, maybe more government involvement in promoting technologies like this would go a long way in introducing blockchains in more areas of our lives. Moving on to some challenges, of course, with all of its benefits, blockchain is not without its challenges. Nikhil, do you want to take this, or?
Yeah, I could definitely. So, all nascent technologies face challenges. Challenges here, they could be arising due to lack of training in the said department, like Apoorva just mentioned, or lack of motivation and what do you say, funding from the right stakeholders, or lack of government inhibition and standards. So, a few points to touch upon. There is scalability. I told you that decentralized systems can be scaled vertically and horizontally. But a blockchain, which is a combination of both these systems, still has problem scaling. This generally happens because of the large sizes of the blocks and the blockchain. So, if one had to mine on Ethereum, they would have to download up to 1.1 TB worth of data onto their personal systems, and that 1.1 TB worth of data is the initial Ethereum chain that is existing, and for you to validate all your transactions on that, it would increase more and more amount of data in your system. Now imagine if this is just one miner on one system, and if there are hundreds and thousands of miners all across the world. So you can imagine how many petabytes of data blockchain would consume. And there is a study which cites that by the end of 2025, that is in another 4 years or 5 years, we would have thousands of petabytes worth of data generated from blockchain systems alone. So due to its very high, storage space requirements, it has a problem scaling up and vertically. So until there are new innovations like, let's say, directed acyclic graphs, those are lower on space complexity and time complexity, and those could be the kind of solutions which might eliminate these challenges from the blockchain technology, which might further, help improve the adoption of the technology. Concurrent transaction speeds. So if all of you, ladies and gentlemen, previously remember, we saw a chart with the various consensus mechanisms and the amount of concurrent transactions that they could handle per second. So the most famous cryptocurrency, as all of us know right now, is Bitcoin. And the proof of, the consensus algorithm that Bitcoin uses is proof of work. Proof of work, as of today, can handle a minimum of only 7 concurrent transactions per second. So only 7 people around the world can transact in the same network in a second. Whereas in UPI or any other traditional banking systems, the numbers can go up to lakhs, millions, if not more than that. If that congests the, upper limit, it can still go up to lakhs of, concurrent transactions per second. And that is one of the major challenges that, blockchain technologies and, cryptocurrency technologies have to improve upon if they want to actually compete against traditional monetary and traditional financial systems, and if they want to break through these traditional strongholds of banks and adopt cryptocurrencies as the new tokens. Mining pools are a very interesting set of people. So if you could go over to the internet, open a browser tab right now, and if you check what are mining pools, or who are the major mining pools, it would show that China controls 81% of the complete mining pool for Bitcoin. So this doesn't mean, the Chinese government has control over Bitcoin. No. But most of the miners, most of the people who, perform the mining and the validations on the Bitcoin networks, most of the people who dedicate their hardware devices for this purpose reside in China. And they have formed groups among themselves. So I cannot name a few of those groups because it might be confidential and some of them are difficult to pronounce also. So there are quite a lot of groups which form the mining pools. What happens when these mining pools are formed is, let's say you and I are a part of a cult or a mining pool. I perform a transaction, and since you have a majority stake or you are a mining pool in that said network, you can validate my transactions without the interference of the other nodes. Because here you have the higher authority, because you have the most compute power. Like this would be very prominent in a proof of stake uh, consensus chain. So let's say that you have 30% of the power, you are the biggest perpetrator, you are the biggest player in that network, and you are my friend. So when I come up to you and I tell you that I will perform this transaction, please validate for me. And let's say on moral grounds that you actually accept to it, you can directly validate even illegal transactions without the interference of the other nodes. So mining pools are a collection of people or computing devices, computing hardware that control most of the system, or control a major portion, major block of the validation and the certifying system in a blockchain network. Incentives. So, who doesn't like incentives? Every morning, I remember my mother used to wake me up early for school, and the only incentive for me to wake up early is that I would get more chocolates. We are trained with incentives, as a goal from the time we are young, from the time we are kids, from when we become adults, even when we are old. Incentives always, culturally appropriate to a human. So even for miners, when they validate transactions, so we have been speaking about miners validating transactions till this moment. But why are miners even performing this? It's because they get incentives. When they validate a transaction, when they mine a block, or when they add a block to the blockchain, they get a part of a cryptocurrency in return. So let's say if I validated 100 transactions today, I might probably get 2 bitcoins as a return for the work I have done, and that is my incentive. I can later use these bitcoins for trading or for like further investing in the same network. That is the personal use that we can speak of in another time or session. But incentives are the constant role of why people are still mining the cryptocurrencies instead of overtaking them with all the hardware power they have. So if the adoption rate is very very high with the current systems, every miner would have to get an incentive. If not, there would be no use of him mining. No one would want to do any kind of no one would want to dedicate their time and resources for free. This is not an open source work, or this is not a charitable trust that they are running. This is a financial transaction cryptocurrency system, and they of course have monetary or other financial motives which they want to gain. And a lack of incentives, or cutting out the payments to these kind of miners or validators, would only anger them and make them turn against the crypto network and bring it down eventually. Lack of exposure. So Apoorva has already mentioned it to all of us, that lack of exposure could be either political backing, institutional backing, educational or literacy, lack of literature in the respective technology, that is with respect to blockchain. So if a person doesn't know how to use a so and so technology, he would never think of its implementation for any new problems that he finds. And even learning about a technology will not directly help you gain uh, solutions to problems right away. More time on research, more time on R&D, and more investment into the cause will help us progress the blockchain to newer further and newer areas from where you can implement it on a daily basis. We have already spoken about energy consumption and how much blockchains consume energy. So let's say one computer system, uh, let's maybe take the example of Dr. Anand, who was showing us his personal computer system, which he uses, the rig that he uses to mine cryptocurrency. Let's say that is a black box system. We don't know its configurations, but what we know is the amount of compute cycles and the amount of GPU cycles it takes. And since it takes a huge number, in its millions and millions of cycles per second, since it takes huge amounts of cycles to perform, and all these transistors are semiconductors which rely on electricity, it draws in huge amounts of power. And these huge amounts of power can easily cost a lot. So a few states in the US which have highly cheap electrical pricing. So the state of Illinois has, uh, please correct me if I'm wrong, has a rate of 4.35 cents per kilowatt hour, and this was, I think, a standard up till last year, and that is the cheapest in the US. So if a person had to just pay 4 cents for a kilowatt hour worth of energy consumption, it would be much better than mining in another place, let's say Washington DC, that charges $2 per kilowatt hour, he is able to mine 5 times the, you know, or he is able to perform 5 times the computations and calculations of a person who is living in Washington DC. And this solely bears down to how much electricity bill they are willing to pay. So energy consumption is a huge limiting factor as of now, and more research in making this blockchain technology efficient will also, bring down the memory, requirement that it has, and also the energy consumption requirement that it poses. And lastly, but one of the main and touching topics, lack of standards, lack of regulations, and no compliance rules. Like Apoorva was mentioning, if there is no standardized, governing body saying that you cannot steal this data, you cannot ask for this data, you cannot store any such certain private data, if there is no governing body which ensures that an organization or any system that is implementing a blockchain implementation, if an organization doesn't oversee this enterprise which is foraying into cryptocurrency, this enterprise has complete control of the system that they are deploying. This means they can ask the users to join their system on the enterprise's rule set completely. They will give their own privacy policies, and if the user does not want to agree to it, he can just leave the program. He would not have to. Uh, he cannot. He does not have any certifying authority to complain to, saying that they have unjust rules and they are not letting me take part in the system. So when you do not have regulations, when you do not have rules set in place, you can naturally, imagine a lot of havoc coming into picture. And that is the same with blockchain technology right now. Why do you think, Bitcoin surges prices very steeply up and down? Why do you think it fluctuates so much? It could be $35,000 a coin one day, probably due to certain inherent factors. It could just drop down to $2,000 in a couple of weeks, and that is a huge fluctuation. And there is no certain body which is regulating how this is fluctuating. It is solely based on the number of peers in the network, number of miners, number of users, and how they are implementing their systems. So this technology, when we can regulate it without ensuring that there is a lack of privacy, or without taking away any of its security features, when we can maintain transparency, privacy, and security, along with that, if you can factor in regulations and standards that we have to involve, that's when I think blockchain would be a more nascent, or a better, well off, mature technology which we can implement for a lot of purposes. So with that, we covered a few of the major blockchain challenges that we face all across the world. So Apoorva will tell you more about the transactions now.
Hi, am I audible?
Yes.
So speaking of incentives, my incentive to finish this fast right now, because I'm sure we're all very hungry. Uh, I'll just cover what a hash is, a block is, and a blockchain is, and a little demo about how it works, a basic demonstration. So I'll maybe take the next 5-10 minutes of your time. Uh, so hash, as we all know, in terms of cryptocurrency, it is a map of a given input, and that is output into a fixed length digest. For example, MD5 hash produces a 32-bit digest, and Bitcoin in particular uses a 256-bit hash, that is SHA 256 algorithm. And by the property of hashes, we know that it should be easy to convert an input into a hash, but given a hash, you should not be able to find the original input. It should be very difficult theoretically, and collision free. For example, if my input apple results in a hash, an input let's say orange should not also return the same hash. And also, if I have two very similar sounding words, they should still result in a very far apart hash so that they cannot be traced back into the same closely sounding words. So by the property of these hashes, it forms the foundation for how blocks and blockchains work, because we want to make it as difficult as possible to break into a blockchain. And with the multiple interlinking of these chains, and that is a hash of a hash of a hash, it would be that much difficult to tamper with the blockchain and break into it. So uh, what is a block? So we already talked about a transaction being represented as a block. So this transaction has the data of what is happening in the transaction. And let's say somebody ABC is transferring $1,000 to XYZ. And also along with that, there is metadata like the block number. What is the series of the block that is appearing within the blockchain? There's a nonce that is generated, and timestamp when the transaction is occurring, the size of the entire block, the hash of the previous block, and the Merkle root. Here, the Merkle root is the hash address of the first block of the blockchain. So this allows the block to be tracked to the a particular chain. It is kind of like an identifier. So when we say hash of a block, as we already know that inverting hashes is difficult as is for a simple input, imagine inverting an input of all of this data combined. It makes it that much difficult to find tamper with data when this entire block data is being hashed all at once. So blockchain is a continuous linkage of all of these blocks that have been generated. So all of this data is hashed, and that hash it is like a linked list with extra steps. Instead of storing a pointer to this, it stores the hash of this. So I'll just show you a little demonstration by blockchain enthusiast created here. So like we discussed, hashes should be unique for a unique input. So I say, as you can observe, as I'm typing, this hash is also changing. New data. So each time I type it, it is very different. Every time I add a new alphabet, a new character, it is resulting in a completely new hash. And let's say I see the hash for the word tell. This is a hash that is generated, and let's just change one alphabet, make it tall. This is a completely different far apart hash, and this makes it that much more difficult to separate similar sounding or similar appearing words. So now we have the foundation for a block. So what is a block? You could try this out in the on your own time as well. I will send the link of this in the chat. So as this is a very simple representation of a block. In reality, this would actually have a lot more data like a timestamp and a lot of other identifying values. But just for representational purpose, this is a very simple hash. So simple block. So let's say Apoorva sent Nikhil 1000 INR. So now you can see that this block has turned red, which is a representation that this value that has been generated, it is not adding up with all of the data in the block. So the block number, the nonce, and the data, they are not the hash is computed on just the data, but it is not in line with the other data within the block. So when I have to mine it, I'm trying to find a suitable nonce value so that a hash is generated that would satisfy all of these other data. So this would take a few seconds. So now a completely new hash is generated along with a new nonce while keeping my data as it is, as I've entered it. So imagine this entire hash in a chain format. So I am linking all my hashes. So as you can see, this hash is the previous hash in this block, and this hash is the previous hash in this block. So 0012FA, 0012FA, and so on. So this chain is a representation of 5 blocks. So let's say I want to attack this and I want to tamper with this data in this block. Let's say uh, fake transaction. That maybe I could say Nikhil owes me $1 million. I'm trying to introduce that transaction as a record within this block. And as you can see, not only is this block resulting in a false hash, all of the resultant blocks that are following this block are affected by this change in data. So for me to correct this, like we did in the previous block, I will try to mine this. Okay, I got a suitable hash for this. And although my new hash, the 000AA, is already copied into the subsequent block, it is still not fixing my tampering with the previous block. It is still showing me a faulty value of the hash because it is not coinciding with the rest of the data, because this hash has changed. So again, for an attacker to rectify fake transaction, they would have to mine all of the blocks in the rest of the blockchain, so they cannot tamper with this. This is what leads to the immutability of it. So technically, theoretically, we can see that here I am showing this with a very limited data. So even if I mine this, I can go on and do this in like a couple of minutes. But imagine this on a larger scale with millions of blocks, with millions of users validating this, and a lot more data within each block. And this would result in a significantly higher time to mine each of these, to correct each of these block values. And by the time that by the time you can take to rectify all of your, to hide all of your false fake transactions, somebody in the network would have identified this, because all of the other blocks are already alerted of illegal change within the block. So this prevents an attacker, this kind of let's say the attacker does not have the motivation to do this, because they would be spending so much compute power to rectify each of the block. So instead of spending their compute power on this, they would rather use it for a good purpose, that is to validate the existing transactions, so they get some kind of profit out of it. Instead of profiting out of a false transaction, they would rather profit out of mining the data, where they're receiving some kind of cryptocurrency as a reward. So this is the whole principle behind cryptocurrency and blockchain, where it makes it immutable and it makes it better, that much more secure, and you cannot tamper with it unless you have sufficient compute power. That would theoretically be thousands, millions of supercomputers and a lot of years to do that successfully. So that will be the closing of this session. We will see you again in the session 3. Thank you for being such good listeners. Yes, I will send the URLs.
Thank you. Thank you very
Thank
much,
you, Nikhil, and thank you, Apoorva. I think we will just have a break for our lunch. Is 2:45 okay, Nikhil?
Apurva ma'am, we would like to, hello. Apurva ma'am, we would like to have this last 10-minute session again from you, so that we can practice ourselves. Otherwise, theoretically, we cannot absorb many things. But if we will do it practically ourselves, then we can have many loopholes which we can discuss with you. So I would request on behalf of every candidate that in second half you start with this, so that we can have a hands on ourselves. This is a
Uh,
request.
yes, thank you for that input. I have sent the link of the demonstration in the chat. You can
Okay.
have a look at that and play around with it. We will also be having a hands-on coding session later.
Right,
We'll
right, ma'am.
teach you how to make your own cryptocurrency
Right, ma'am.
simulation, sort of. So
Right,
uh,
ma'am.
I'll send the link of the Satoshi Nakamoto paper also. You can have
Right.
a look into that.
Ma'am, other than that, link of your mail ID so that if we have any doubts, we can mail you that also
Yes,
without
sure,
disturbing the activity. Thank you, ma'am.
sure. Yes, thank you.
Thank you, ma'am. Thank you.
Thank you. Nikhil and Apoorva, shall we meet at 2:45?
Sure,
Yeah,
sure, sir.
sure, definitely.
Yeah, participants, we all will meet at 2:45. The link is already shared. The link is different again. We all will meet at 2:45 again. Thank you. Thank you,
Sure.
everyone.
Thank you.
Thank you.
Thank you, sir. आपका नाश्ता बना रहा हूँ।